Thanks. So I missed my chance to introduce myself at the introductions earlier. My name's Alexa Van Eaton. I'm an NSF postdoc working with both Amanda Clark at Arizona State University and the U.S. Geological Survey. And as was sort of alluded to in our first talk, this problem of particle aggregation has become a kind of emerging topic in volcanic ash dispersal challenges and questions. And so what I'd really like to see if we can address here is how the role of eruption style kind of plays into this process. And so I'd really like to acknowledge my co-authors, and especially equally contributors Larry Maston and Christy, and a couple of others who've really contributed to the development of these ideas. So what we're talking about here in terms of ash dispersal, we classically think about the movement of volcanic products as being a size-differentiated process, whereby the finest particles have the longest residence times and get dispersed the most widely away from the source. But what actually happens when aggregation is taking place is that those finest particles stick together as clusters. And this fundamentally changes the dynamics of the moving ash cloud in that those particles that once had residence times of weeks to maybe years are now falling out nearly immediately or on a time scale of sort of hours to days. And so this process really is at the core of a sort of first-order control on ash dispersal in the atmosphere. And it's becoming more and more widely considered that it may be that all fine ash particles are involved in this process to some extent. So what do these actually look like? Ash aggregates have like a huge range of morphologies, and really in terms of, there are two main processes that stick them together. Electrostatic attraction is on the water pore end of the spectrum, so particles can be stuck electrostatically through an electric charge. And that's sort of like these loosely bound, fluffy types of clusters that tend to break up on impact with the ground. And the increasing amount of water content that you get involved in your system, you can start to develop these beautifully concentrically layered, sort of coherent accretionary lapili, all the way through to mud rain, which splashes on impact with the ground. And in terms of the actual quantitative impact that this has on the dispersal of volcanic products, we can use an example from Readout, which Christy and I have been working on recently, an eruption from 2009, where we were sort of able to quantify the sizes of the particle aggregates that were involved. And so when you're talking about an erupted grain size distribution that looks something like this, averaged over a bunch of samples collected over a wide range of the dispersal area, you can see that you've got particles from around a micron all the way up to a few centimeters. What happens during the airborne dispersal of those products is that the very finest ash particles turn into really huge clusters or aggregates. And in terms of what that actually kind of looks like, we're talking about converting particles that are less than a couple of hundred microns up to a couple of millimeters to centimeters. So this is really can be a first-order control on where the ash cloud goes, and even its detection and remote sensing. So we can see that this is something that volcanic ash forecasting models are starting to think about and integrate into the sort of physical process that's being calculated. And also in terms of the physical volcanological processes, so using an interpretation of those volcanic layers to extrapolate what actually happened during the eruption. The formation of these particle aggregates tend to be associated with water involvement at the source, and it can actually give us a sense of if a deposit was emplaced by a pyroclastic density current or fell out of the sky, sprinkled as fall deposits. And there's this emerging question of if aggregation can affect actually the climate impact of volcanic eruptions. So if you have rapid scavenging of aerosols and particles out of the atmosphere, can that actually decrease or change the climate impact of a volcanic eruption? So these are some of the questions that are starting to be looked at in the physical volcanological community. So what we can look at here is where and when does aggregation occur? When have we seen that happen? How does it actually play into this feedback between atmospheric and volcanic processes? And what do we need to think about when we're fine-tuning and developing these models for long-distance ash dispersal? We're going to look at a couple of examples. We can look at Eyjafjallajökull, the overall kind of drying out of that eruption, and how that impacted the ash aggregate structures. We can look at this example I referred to earlier from Redoubt Volcano in Alaska. And if we have some time, to look at some of the really big ignimbrite forming eruptions and how the aggregate structures change throughout these different eruption styles. So many of you are probably pretty familiar with this eruptive sequence, but in general, as sort of set out by Magnus Gudmundsson, the first explosive phase of the eruption was the most phreatomagmatic. There was extensive interaction with the glacier and a little bit more water involvement than the later sequences. The products of these deposits, the products of these phases of eruption, were, you can see here, interlayered with meteorological snow. And if we just zoom in on one of these spots, you can see that interspersed with the snow are little tiny 1 to 2 millimeter ash-infused hailstones. And as you go upward through one of these darker looking sequences, you see more traditional accretionary lapili. And so this suggests that there are processes happening in volcanic clouds that represent a spectrum between hail-forming processes and what we consider more ash-rich end members. As the eruption became a little bit more dry, there was less interaction with that glacier. As documented by Costanza Bonadonna and others in 2011, there were much kind of smaller, weaker ash aggregates falling out of the cloud. There weren't sort of the concentrically structured accretionary lapili or hail falling out, as much as there were these smaller little balls known as kind of ash pellets. And then, documented by Jacopo Terrucci and others around the same time in the last explosive phase of the eruption, we take a look at their video, which is pretty cool. I don't know if you can see that really, but you can kind of see these little tiny ash clusters that were falling out and breaking up on impact. Maybe we'll just show that one more time. Or maybe not. But the general trend is that as the eruption started to dry out, the ash aggregate structures fundamentally changed. Now, comparing this with what has been documented at Redoubt, the Redoubt volcano eruption in 2009, which you can see here on the map, we're looking at, kind of the armpit of Alaska, Redoubt volcano, Anchorage over here. This was also a really phreatomagmatic eruption. There were icy lahars spewing out from the amphitheater. The fallout was totally aggregate dominated. And this is because there was a reasonably thick snowpack and glacier in that crater amphitheater. And there may have been other water sources, potentially from glacial stored melt in the edifice itself, and then the sort of snow and ice cover around the edifice. But this was a very phreatomagmatic eruption. And the deposits aren't incredibly dissimilar to what we saw from Eyjafjallajökull and Grímsvötn, actually, in that you see meteorological snow interlayered with more concentric aggregate structures. So if we kind of zoom in on this spot here, you can kind of make out that there are these ash-rich structures, and then just like what we saw previously, little ash-infused hail falling coevally with those aggregate types. And so again, we see that there's this sort of feedback between a meteorological process that we're really familiar with, sort of snow and hail formation, and then the formation of aggregates. So if we do thin sections of these guys and extract water contents from the accretionary lapili themselves, we can start, I think, to get a sense of how much water may have been involved at the source, a sort of snapshot of how much water was falling with the deposits. And by looking at the internal stratigraphy structurally, we can start to develop an idea of how many cycles these aggregates experienced during their growth cycle. So what we've done recently is use some of this information to initialize a three-dimensional numerical model of what processes may have been occurring or may have been stable in this eruption cloud from Redoubt volcano in 2009. So this is an example of one of these simulations. And what we're going to see here, so this is the overall extent of the cloud. We're looking at Redoubt volcano sort of towards the west, that most of the plume is heading towards the north. And what we can resolve in this model is the formation of precipitation, so rain and hail. And looking at the stability of those different water phases, get a sense of where aggregation might occur in this process. Oops, let's actually look at the video. So you can see that the eruption column rises up, and this purple stuff is the hail, falls out really rapidly close to the source, so then sort of 20 to 30 kilometers north as the rest of the plume continues mostly towards the north. You can see there's a bit of wind shear here where the upper portion of the plume is heading south. If we compare this with the radar data that was collected from the eruption, we get a pretty good match between the simulated plume heights of the coarse particles and the hail with the actual measured radar. So the dots are the radar, and the dashed line is the model result. So it's a pretty solid match. What's totally separate is the fines. So what you can see here is that through time, after about 8 or so minutes, the coarser particles are decoupling in the atmosphere from the fine ash that escaped the aggregation process. And so this is really interesting from a sort of detection perspective, because it suggests that the fine ash was not seen by the radar, which is not surprising to a radar operator, but kind of surprising to a physical volcanologist, because we tend to use these radar plume heights as a very clear indication of where the plume went. But in fact, when you have processes like aggregation happening, you get a much more dilute, potentially fine ash cloud signature that totally escapes detection. So this is potentially something that is not just important for long-distance dispersal of ash, but actually the detection of the eruption plume itself. And the fine ash cloud from this eruption actually was there, detected in satellite some hours after the actual injection of ash into the atmosphere. So maybe in terms of what we can think about for these sort of moderate-sized eruptions, is that when we have a very wet source, so a glacier or a lake, a lot of that aggregation is going to be happening in the vertical updrafts and in the near source umbrella of the eruption plume. And so you can get rapid proximal aggregation that just pulls fine ash out from the plume near source. Whereas in contrast, if you have an eruption that's from a dry source, like in the later phases of Eyjafjallajökull in 2010, you're not necessarily going to get really proximal material falling out, but you will get meteorological interactions that can happen somewhere downwind. And so this is potentially a useful framework for thinking about these different morphologies of aggregates that we often see falling from clouds and in the geological record. So thinking about the big eruptions, Oruanui was the most recent super eruption that we've had, around 25.4 thousand years ago. And I did my PhD on this topic in New Zealand. It comes from Tephra volcano, right here in the middle of the North Island. And you can see that Lake Taupo is here now. This present geometry of the caldera was excavated by this eruption 25.4 thousand years ago. But also, there's sedimentological evidence of an ancient rift-related lake that was elongate in the central North Island, also known as Lake Hooka. And we know that the eruption interacted with this lake extensively. It's totally phreatomagmatic throughout. And How we know that is a couple of ways. One thing that Colin Wilson likes to say about this eruption is that despite its size as a super eruption, more than 80% of it could fit through the mesh of a tea strainer. It's so fine-grained. So it's freakishly fine, presumably partly through interaction with that lake water. It's full of ash aggregates. And we also recently found that it's also full of diatoms, primary diatoms from the lake sediments themselves. So some of what we can actually see in the field from a physical volcanological perspective, we're looking at, for example, this site 12 kilometers from source is proximal for unit 3 out of 10 units defined by bedding. And then this photograph here is from 85 kilometers, which is more distal for unit 3, where it starts to transition mostly to a fall deposit. But what's really intriguing in the ignimbrite for unit 3 is that you see these beautifully concentrically layered aggregate structures, accretionary lapili. And then as they transition away from source, they become much more weak little particle clusters in the more distal area. And you can also see up here in unit 8, the scalped base of a very aggregated bed scoured by ignimbrite at the top. So what can we make of this? How can we use those aggregate structures to distinguish sort of dynamic processes happening during an eruption? Two just very simplified end-member observations are that the fall deposits tend to be associated by with this class-supported framework of weakly concentric structures. So you can see that they're kind of just falling right on top of each other. They have an open work framework. You can see that there's some weak layering in there, but most of them are massive. Whereas in the ignimbrite, in the laterally emplaced material that came in as a pyroclastic flow, you see matrix-supported, much more complex accretionary lapili. And these relationships hold in big ignimbrites for, as far as I've been able to see, for almost every big ignimbrite-forming eruption. These are sort of universal characteristics. This is something that still needs to be tested, and it's an active area of research. But these, this is potentially very useful to be able to distinguish fall from flow in a deposit that otherwise looks pretty much totally homogeneous. And so the evolving model for how these types of really complex accretionary lapili may form is that in a big eruption where you have both a powerfully spreading umbrella and voluminous pyroclastic density currents, in the sort of vigorous vertical updrafts, you have fallout of those more massive little pellets, accretionary lapili, that then fall through the buoyant vitric ash elutriating from the pyroclastic density currents many kilometers from source. So you essentially have an ash-choked atmosphere through which the accretionary lapili fall. And then when they fall into the actual flow that may or may not still be there, traveling along the ground, they break up. And so you see these associations in many different ignimbrite packages. So what this means in terms of a sort of thinking about process or hazard assessment is that whereas in a unit that would previously be mapped as pure ignimbrite, as a pure pyroclastic density current deposit, you can actually start to tease out breaks, time breaks, in the deposition of that unit by finding actually fall layers. You can see you can't really tell that that's made up out of class-supported aggregates. But if you pull it out and look at it in the lab, or look at it really carefully in the field, usually the lab is better, you can see that they're so this deposition of this bed in the ignimbrite, or in the pyroclastic density current, was interrupted long enough for the pellets to fall out of the air. And so this potentially changes the way that we think about the buildup of ignimbrites and the mapping of hazards around a volcano, if we can think about how those aggregate structures tell us what was actually falling at the time. So this is the idea. This is something that's still developing and being tested, but we can use these structures to distinguish fall and flow, to look at pauses and episodicity in the deposition of these deposits and their formation at the source, and potentially that they indicate a really, at least in these big ignimbrite-forming eruptions, sustained interaction between overlying plume and a ground-hugging flow. And just as a quick slide here, something that we're currently working on now, known as the TBJ, the Tierra Blanca Joven, from Ilopango caldera in El Salvador. This is an eruption that's around from 536 AD approximately. It's really similar to the Oruanui eruption in that it's interlayered fall and flow. It's voluminous, so between 50 and 100 cubic kilometers bulk tephra, and it interacted with a huge lake at the time of eruption. And so this has a kind of archaeological impact because it displaced the Mayan communities right around the area, and it potentially had a global climate impact. This is something that we need to look at a little bit more carefully and maybe talk about ice core records, but something that's of interest and maybe a rich area for future research is the extent to which a really wet eruption that's rapidly being scavenged out of the atmosphere by aggregation, if that is actually going to diminish the impact on climate, if it's possible to have a moderate to huge eruption have a global climate signal if it's extremely wet and being microphysically pulled out of the atmosphere quickly. Yeah, I think that's it. Yeah, that's a good question. For the Oruanui eruption, that lake, I mean, there would have been at least 100 cubic kilometers of water available. So, you know, it's not really a big ask to get enough water in the eruption to make it behave really wet. You want maybe between 15 to 25 weight% water for it to start developing coherent aggregate structures. But yeah, one question would be, how does even the injection of water into the stratosphere affect the climate? It's never been constrained.